Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to do is we're going to look at the graphs of solutions to our differential equations. So I'm going to put up three different kinds. The first one that we looked at when we had real roots. I guess we'll do it in yellow, sure. Real roots. And for example, one of our equations was for real roots, we had y, these were null solutions, y equals e, and I'm not even going to put the constants on them. What I want to be able to do is sketch a graph for you. E to the minus t plus e to the minus 2t. Okay, the real root. Then another one that we had here was we had repeated roots. Repeated roots. And for that we had y equals, for example, we had, I think it was e to the minus t plus t e to the minus t. And then we also had complex roots. Those in this icy blue, complex. And they were of the form y equals some exponential. I think we had like e to the minus 1/2 t cosine. I'm just going to use an omega t plus e to the minus 1/2 t sine omega t. Those are the three different solutions that we've looked at so far. And it's important to notice this. When the exponential e to the at has a greater than 0, the solution is unstable. And what we mean by that, we mean that as time passes, so as time goes to infinity, then the solution also goes to infinity. And it does it very fast. E to the t grows quite quickly. Now, here's the other part, though, is when a is less than 0, the solution is stable. And what do we mean by that? We mean that as t tends to infinity, y of t tends to 0. Two ideas are that of like a swing, eventually it comes to rest, or when you're driving a car and you have the shock absorbers, and I'll explain that in a moment. So let's graph these. So what's going to happen is, let's graph the real roots. So if we have a decaying solution or a stable solution, it's going to just come down like this over time. Just like when you first learned about the exponential function. Now, when you have repeated roots, notice that your first term is e to the minus t, and that would come down like you would expect this yellow picture to have done. But notice what happens. The second term is t times e to the minus t. So even though e to the minus t is growing very fast, and t is growing as time goes on, e to the t will bring that t value back down. So what happens, though, is the t at first it kind of gives it a boost, but then as time passes, e to the t overpowers it, and it too will tend towards to zero. Oops, mine looks like it's going back up. It shouldn't go back up. It comes up, and then it's going to come back down. Something like that. And finally, the last one are complex roots. And in the complex roots, we have oscillations while they're decreasing. So in this case, you'd start at some point, and then it's going to decrease, but it's going to decrease and oscillate at the same time. And each time it oscillates, the oscillation gets smaller and smaller and smaller. So this first one we call overdamped. That might be like driving a race car. The shocks are just super uncomfortably stiff. You feel every little rock on the road. Repeated roots give us this green graph. This is called critically damped. This would be like shock absorbers in a normal car, where you feel an impulse when you hit the speed bump or a road, but then quickly the car just stays smooth and levels out. This final I just drew a blank, sorry. Oh, the final one, the one that has the oscillations, this is called underdamped. Oops, wrong color, blue. This is called underdamped. And as cars have gotten better and better, and so have shock absorbers, you don't see this much anymore, but if you ever see a car that when they hit a speed bump maybe, or a bump in the road, and the car bounces for a bit before it finally settles down, they need new shock absorbers. It's because their shock absorbers aren't working properly, and so you're seeing the underdamped oscillations. I hope that helps, and thanks for watching.